Thank you everybody for joining me. I'm going to be giving a talk in this series that's perhaps a little bit broader and maybe a little bit less deep than some of the other talks that we've been hearing in this series. But I'll be talking about some surprising geometry that shows up in the physics of crystals and, surprisingly, the blue sky. And this geometry is all to do with the polarization of light, which is one of the main reasons we wear shades. So I guess this is could be co-titled Topology in Shades. But as it's getting dark here in Birmingham, I think I'll put my regular glasses back on. So what I'm going to be talking about today primarily is geometry of light patterns. And there are many different sorts of ways that we can get patterns in light. It's a surprising thing that light is what we how we see, so it's how we visualize things, but we don't always think of the light itself giving us interesting geometry. So obviously we see light traveling in straight lines in a light beam, or perhaps the colors of a rainbow. This is a photograph taken by someone working for the BBC last week, a remarkable triple rainbow in Gloucester, about 100 kilometers south of Birmingham, and the bright light patterns on underneath the water that I think Renzo talked about in his talk as well, giving us this remarkable sort of geometric patterns that light can have. Now, those are all things that we can see with our eyes, but a lot of what we can see depends very strongly on the way our eyes work. Our eyes are good at detecting intensity and colors. That's why we think a rainbow is impressive. If we only saw in black and white, a rainbow would just be a single bright circle and we wouldn't see all of the beautiful colors. But what it means is there are certain phenomena that we can't see with our eyes, and they're to do with the polarization of light, the direction that it's vibrating in. So here's a polarization effect photographed through birefringent film and polarizers, or stress birefringents, and I can actually try to do this demonstration. Hopefully my demonstrations will work. Hopefully I should have switched to my screen. So this is a device with crossed polarizers. You see the reflection of the camera, but it should look black because the two polarizers don't oriented orthogonally to each other. And so here I have just a piece of plastic, and it looks like it's boring, doesn't have any interesting optical properties. But when we put it through between cross polarizers and I squeeze it, you see a colorful pattern, which is to do with the way that the polarization is affected by the polarization passing through the crystal. The plastic is twisted as it propagates through, and we miss that if I just squeeze the material by itself. But between the cross polarizers, we can see that there's this extra optical effect. So now moving back. So that's a way of looking at the stress patterns that we are using polarization. And in devices all around us, we use liquid crystals, liquid crystal watches, liquid crystals on our laptop screens. And again, that's because of the polarization patterns that they have, that we can manipulate. We can manipulate light to give us the images we see on our screens. So the main idea is that many natural optical phenomena involve polarization, and polarization, being a vector, being directional, is associated with the inherent vectorial or tensorial nature of light and vision. And one of the most surprising aspects of this is the blue skylight is polarized. And again, we see the blue sky, we don't think of it like that because our eyes aren't sensitive to polarization. So what I'll be talking about today is the geometry topology of a simple but very universal pattern that's often found in polarization phenomena and is very related to the skylight polarization pattern. And I'll take you on a journey involving history, apiology, the study of bees, archaeology, mineralogy, navigation, aerology, and etymology. So I'll start by talking about this skylight polarization pattern, what it looks like, and who can see it or have used it. Both bees and, surprisingly, there's a story about a possibility that Vikings did. Then I'll talk about crystal optics and understanding this pattern geometrically as applied to so-called birefringence of light going through a crystal. This leads on to how instructions on how to navigate like a Viking, determining the skylight polarization with calcite, before I'll talk about the skylight pattern in more detail in its relation to scattering theory. But underpinning it all is some very simple geometric patterns that comes from just very simple linear algebra, but not in a way that we often think about it. So start with this skylight polarization pattern. So the first thing I said, etymology. Here's what the Oxford English Dictionary has to say about the word polarize. Well, it was coined by Malus in 1811, just over 200 years ago. And in the etymology, there was a comment saying, in giving to the sides of the ray, so I think the ray travels through space, but there's some sides on which it vibrates. He gave the sides of the ray the name of poles, which imparts the light properties relative to the poles, polarization. This expression signifies the modification that light has undergone in acquiring new properties, not to its direction, but to its sides. But unfortunately, this assumes a sense of pole different from its use in astronomy, geography, and magnetism, with the consequence that polarization as applied to light has nothing in common with magnetic or electric polarization. What that means is where the latter things like electric or magnetic polarization, we think of as a vector with a single arrowhead. But because with light we're talking about vibration both up and down or left and right or whatever, we have what's called a director. We can't say there's a single direction. It's a sort of double-headed vector, both a direction and its opposite. And that underlies the geometry of all of the polarization patterns that we'll be thinking about. So here's a video that I took of myself with a polarizer on a sunny day, just through the blue sky. And you can see that as I rotate the polarizer, it goes slightly bright, slightly dark with different angles. So I tried to align it where it's its darkest, and that line would, so the line is sort of aligned to help me remember that perpendicular to the line is the line of the vibration. So the line is the line that polarizer effectively blocks the light vibrating perpendicular to it. So at that point in the sky, the light vibration is at that angle. And as it happens, the direction of the sun is in a perpendicular direction away from it. But if I look in different directions in the sky, obviously I'm going to have a different orientation, or there's a question what the orientation is, and that sets up overall a pattern of lines on the sky. And it's a natural question, what does that pattern of lines look like? We can't see it, but it's obviously something that's there. And this is something that's actually very important in all sorts of applications to navigation using the polarization of skylight. Historically and originally, it was first studied for bees by von Frisch, who got the Nobel Prize, or shared the Nobel Prize of Physiology and Medicine in 1973 for working out the mysterious waggle dance of the bees. And it surprisingly involves an aspect of that, which is the fact that the bees are using the polarization of skylight to navigate. So he says here, the bees must have been able to read the sun's position from the blue sky. The direction of vibration of polarized blue light differs in relation to the sun's position across the entire vault of the sky. to one that's able to perceive the direction of vibration, even a spot of blue sky can disclose the sun's position by its polarization pattern. And then he did an experiment to show that bees can see polarization. So bees are able to perceive polarized light. The sky, which to our eyes is a uniform blue, is distinctly patterned to them. They use this extensively and, in their orientation, guide themselves not only by the sun's position, but also by the resulting polarization pattern of the blue sky. And then he goes on to say, if it's, or it seems bees appear to us miraculous. But it is now clear to us that ants, other insects, crayfish, spiders, and even octopuses perceive polarized light and use it for orientation, and that among all these animals, it's the human being who is the unendowed one. So it's extremely generic to see polarized light, it's just that we can't see it. So as I said, that the skylight is sort of, we see the sun's there, it's partially behind the cloud, but if we were to say that the vibration is approximately perpendicular at each point in the sky to the point, that if you draw the line from the point you are to the sun, the vibration is perpendicular to that. So you can try to fill in what the vibration would be at each of those points. It turns out, although that's a good approximate guess, that's not quite the full pattern. The polarization pattern is actually more interesting, and here is what it looks like. I'll talk a little bit later about it. The red lines are observations made by Rayleigh from the Annapolis in Maryland. What we're looking at here is a full map of the sky. So you round the edge, you can see there's some trees, and in the middle is the point straight up. So radius into this disk is proportional to the angle going between naught straight up and pi on 2 on the horizon. And about halfway up, there's the sun, which has been blocked out by a mask. And so the red lines are the directions of polarization at each point in the sky that Rayleigh has measured. And the blue lines are an interpolating theory that I'll talk about later on. So what you can see is it's not quite circles around the sun. It's almost like a little fingerprint pattern where there's some interesting point going on above the sun, which is between the bright disk and the center of the disk. And I'm sorry, I can't get my cursor to work, so you just have to follow what I'm saying in words. So that's the pattern that the bees can see and we can't see. And it's very striking to think, if we could see polarized light, whenever the sky was blue, this is what we would see in the sky. So one of the interesting aspects of this story is it's been proposed that although humans can't see the polarization pattern of the sky naturally, it's a very useful thing to follow the inspiration of the bees to be able to say, well, if I can't see the sun because it's behind a cloud somehow, or behind some other sort of obscuring object, I can still make a pretty good guess where the sun is because these lines are sort of roughly perpendicular to the sun. And one suggestion of that's quite interesting is that maybe the Vikings took advantage of this. So in Viking sagas, there are several mentions of something called a sunstone. No one knows what it is, but in the sagas, it seems to have something to do with revealing the sun. And so the suggestion is maybe somehow the Vikings were using the sunstone can detect the polarization of light, and if you're stuck in the middle of the North Atlantic, which quite often is very cloudy, with a small patch of blue sky, you can work out where the sun is and take your bearings from there. And this has been taken up by several people recently, trying to see whether, in fact, it is possible to navigate at sea using this. And This is an example in Navigator's newsletter, Viking Navigation using the Sunstone and polarized light. And this author, Leif Carlson, didn't only write a paper, he also fictionalized his story, Secrets of the Viking Navigators, which can be yours for $9.51 on Kindle. But one of the aspects of this mystery is that if the Vikings did use these sunstones like this, they can't be polarizers. They weren't polarizers like a polarizing film. Until we actually were able to synthesize Polaroid, there was no good way of trying to detect polarized light. Carlson's suggestion is they used the crystal called calcite, also known as Iceland spar, but that's a different sort of material than a polarizer. So if sunstones were naturally occurring polarizing crystals or Polaroid shades, clearly we could just turn it to see the darkest bit. But if we have a piece of crystal like calcite, that doesn't have these properties, so it doesn't obviously polarize light. So how could that work? But an important feature is that calcite is birefringent, which gives it different polarization properties. And again, this is something that, interestingly, people studying physics or geology a few decades ago would have studied a lot more than people these days, and it's quite interesting to see the phenomenon. And so I will move over to my screen just to show you. I have two pieces of calcite here. Here's a small piece, and here's a large piece. And what I've done is I put a marker here, a spot. And if you look through, you can see there are actually two images of the spot going through this crystal, overlapping. And that's what is meant by birefringence. And here with my sheet of polarizer, putting it in between, as I turn the polarizer, you can see the two spots jump. It jumps between the two spots, so somehow these two spots have got different polarizations. So how does that work, and what does that? How would that be able to be used for navigation? So that brings me on to my second part of my talk, but I can stop now and answer any questions if anybody has anything they'd like to ask. Everybody okay? I'll keep on going.
Please.
So so the next thing is, it's actually taken from let's say, was somewhat standard in older treatments of physics of crystals, but often been forgotten and isn't really given the geometric or topological flavor that I'll try to give it. So here's the plaque celebrating James Clerk Maxwell's discovery of Maxwell's equations, which describe the behavior of light. Here they are in vector calculus form. We're talking about macroscopic electromagnetism, so we have four vector fields. This one called D, the electric displacement, E is the electric field, B is so-called magnetic induction, and H is the magnetic field. And these four equations with their space and time variation tell us how electromagnetic fields such as light behave. Now we're thinking about light propagating through a crystal, which has certain special conditions. So the magnetic induction is proportional to the magnetic field by a constant mu naught, a universal constant. Also in a crystal, there are no free charges, so rho, the thing divergence of D, equals 0, rho vanishes, and the J on the right-hand side, the free current, vanishes in a crystal. So those are the equations we want to solve. So we're thinking about crystal optics, and in the crystal, the important thing is that in the crystal lattice, different directions look different. And that's summarized by the fact that D, the electric displacement, is linearly related to E, but linearly related through this dielectric tensor, effectively a 3x3 symmetric matrix. Symmetric matrix for the sort of crystal we're talking about, which is calcite. So an interesting question is, what's the relationship between D and E? And of course, that's a very simple to picture because it's just a linear relationship. If we start with, well, a vector V and multiply it by a symmetric matrix M to get U, U is related to V if V lives on a circle by an ellipse in 2 dimensions or an ellipsoid in 3 dimensions, where the axes of the ellipse correspond to the eigenvectors, and the eigenvalues correspond to the lengths of the semi-axes of the ellipse. So whenever we have a linear transformation, we can always visualize it somehow as an ellipse or an ellipsoid in n dimensions, where the eigenvectors and eigenvalues are related to the axes of the ellipse or ellipsoid. And any vector that's not along an axis has its direction changed. So that's what we might expect from Maxwell's equations, and these are different effects that we might see in different sorts of crystals. So what happens is, as light enters a crystal, it has a certain polarization direction, and it turns out there's that polarization gets resolved into 2 orthogonal eigenpolarizations. Each eigenpolarized ray propagates in a slightly different direction, and that's why you see these 2 images here, the word calcite at the bottom left, and the eigenpolarizations, the different waves propagate through the crystal at different speeds, which means when you look at them through cross polarizers, as in the center and the right hand side, you get interference patterns. So how does that work through Maxwell's equations? Well, we're thinking about E, D, B, and H. We're thinking about just a regular wave propagating through. So the spatial and temporal dependence is just a plane wave. Direction S is a unit vector. K is 2 pi over the wavelength, and omega is the frequency. And so we choose our direction S that's propagating through the crystal. Because we're assuming that space and time dependence just appears in that exponential form, we can substitute all appearances of the del with IKS and all time derivatives by minus I omega, which means Maxwell's equations take on a slightly different form. The first 2 tell us that D and B are perpendicular to the propagation. And that's why we use D and B, which is different from E and H. And the other 2 have cross products, which came from the curls. So we're going to use D, the electric displacement, because that's the thing perpendicular to the propagation direction. So by Maxwell's equations, we can say that D is proportional to minus S cross B. Substitute B from another one of Maxwell's equations, we get it proportional to minus S cross E, and we can substitute E for the inverse epsilon dielectric tensor dot D. So when all's said and done, what we're saying is that Maxwell's equations require that the D vector is minus dum-de-dum-de-dum D, which you can think of as a matrix eigenequation for D. There's a matrix minus S cross, and there's an eigenvalue which is related to the refractive index, the speed of the wave in our given chosen direction S. So we found the plane wave solutions of Maxwell's equations in the crystal if we can solve this matrix eigenequation, where P perp S is the projection into the plane perpendicular to the propagation direction S. So even if you didn't follow all the details, here's where the real geometry begins. What we're saying is that the Ds that we're interested in are the Ds that are the eigenvectors of this operator in brackets. And what is the operator? It's a projection on the left and the right of our matrix. And what does this do? This is actually just what we do when we look at something, when we visualize it. that here on the screen is a representation of an ellipsoid in 3 dimensions. But if you were going to draw it with a pencil, what you would draw, its outline, is actually an ellipse. And the ellipse is what you get when you project your ellipsoid into the plane perpendicular to S. And for different choices of S, different choices of line of sight, you get different ellipses in 3 dimensions. And those ellipses are related with 2 axes. And you remember these 2 axes are the eigenvectors that we started with. So this is a construction in crystal optics going back into the Fresnel in the early 1800s. So it's called the index ellipsoid or the Fresnel ellipsoid. And different sorts of crystals have different sorts of epsilons with different properties. So there's 2 sorts of crystals that show up: uniaxial crystals, where the ellipsoid is an ellipsoid of revolution, and that has an axis, which is the long axis, everything else, the axis of rotation of our ellipsoid in the uniaxial crystal. And you can see that however you would look at that ellipsoid, what the projection that you see into the plane perpendicular to your looking always gives you an ellipse which has one of its axes parallel to the projection of the main axis. But if you look right down the middle, what you see is a circle. And a circle is degenerate. It doesn't have any well-defined major axis or minor axis. So it's a sort of singularity. It's a degeneracy in the space of directions. And that's what's called an optic axis. This is uniaxial because there's one optic axis, which is the direction of revolution. Now, there are biaxial crystals as well, and this is the generic situation where you have an arbitrary positive definite symmetric matrix. And although you have 3 different eigenvalues, you only have 2 optic axes, in the same sense that for any arbitrary direction of looking, I will see an ellipse with a major axis and a minor axis. And if I look along an optic axis direction, it appears to be circular and there is no major or minor axis. And this, what these axes are related to, is this slightly unusual representation of a symmetric rank 2 tensor as some amount of diagonal plus a symmetric combination of 2 unit vectors u and v. So this isn't amazingly well known. It's not necessarily standard in linear algebra to think of matrices like this, but it is actually something that was well known historically and was originally studied by Maxwell again. In a general case, he was actually thinking not just of ellipsoids, he was thinking of a general multipole, i.e. an eigenfunction of the Laplacian on the sphere. And he made some claims that were proved by J.J. Sylvester that says that any eigenfunction of the Laplacian on the sphere in 3 dimensions can be represented by a set of monochord multipole vectors. So for a function f on the sphere of theta and phi, we're corresponding to eigenvalue with label L. I have this superposition of spherical harmonics, which have to be real. So that's what there's a condition on the coefficients. But Maxwell and Sylvester found that this f can always be represented as a sequence of directional derivatives. There are L directions, L poles, L multipole vectors for any given f. And you take the directional derivative in those directions, you get exactly the same function in theta and phi. So here's an example for L equals 10, but going back to L equals 2, these correspond to the optic axes of our ellipsoid. So if we look around an optic axis, uniaxial, we will see, when we look at the axes of the ellipse, we'll see a pattern like this, which looks like circles and radial lines. And if we put it between crossed polarizers. The polarizers would say filter out the horizontal and the vertical. You can see that that will black out both the vertical line through the middle and the horizontal line through the middle, which is what you see when you look at a uniaxial crystal through crossed polarizers. The biaxial case is rather more complicated. Rather than having this sort of polar coordinate type structure, instead there's this these parabolas, these nested parabolas around the point. If we put that between crossed polarizers, blocking out, say, horizontal and vertical, you can see that the only lines there which are horizontal and vertical is the vertical line through the middle. And if you look at a material like that through crossed polarizers, you see a single line through the middle. Uniaxial case, you get this cross. And here's a visualization of that in days before computers, done by hands from a textbook on optical crystallography from the 1950s. And I won't talk about this in detail, but you can use the same sort of geometry, not to look at the propagation of the S direction, instead the direction of the energy flow, which is the cross product not of D and B, but E with H. So we have to go back to our ellipse from D to E, and then perpendicular to E gives us the direction the light propagates through the crystal. And that's different for our two directions, so why we see these two images of what's on the other side of the crystal. So perhaps slightly hard to follow a lot of the details, but you get the idea that everything is all of these optical phenomena are simply boils down to thinking about projections of this ellipsoid attached to a crystal. So before I keep on going, does anybody have any questions they'd like to ask now? So I keep on going.
Yes, please.
So, okay, so returning to the issue of how might Vikings have used the polarized light with calcite, we can think of taking our calcite and putting a marker on it. So I'll return to my calcite sample. So here I've just put just this this line marker on it, so you can see that there's these two images in the birefringent line of the calcite here, and as I rotate the polarizer, you can see that it jumps in its position. So and this was as originally described in the discovery of birefringence in the 1660s by Bartholinus. It notes that it's in a particular direction associated with the crystal structure. So if we take our crystal and we put our marker on it, we can choose it. We can, with a given polarization, we can see that the two images of the lines are in parallel. But if we were to rotate the crystal against the illuminating polarized light, because the two polarizations are perpendicular, we'll get a superposition. Well, they'll be vary in strength, the two lines. And I'm not going to try and do it in the demonstration here, but I've got a previous movie I made of the crystal. You can see as I rotate the crystal, one of the lines becomes more strong and the other becomes weaker. And trying to find the direction in which one of the lines is strongest and the other line is the weakest, which maybe you have to do with your eyes, that gives again the direction of the sun. So I thought that was a demonstration that more or less the same direction where this one is the weakest and this one is the strongest, which is the same direction as using the polarizer to try to work out what the direction of the sun is. And more careful measurements than that demonstration have claimed around a 1 degree error that is possible if you're trying to do it from the deck of a ship. So that shows at least that there's some using the geometry of polarization in birefringent crystals, we can understand something about the geometry of polarization in 3 dimensions. But let's go back to thinking about this skylight pattern that we started with. And here are Rayleigh's measurements again, as I said. And you can see that the pattern, the red lines are the direction of polarization measured, and he's put black spots where actually there is no discernible direction to the polarization. And zooming in, we see a pattern where maybe similar to what we saw before around the optic axes, in the center of it, there's no unique direction, and nearby we get this parabola pattern of the polarization lines. And these points, these 2 points in the sky, the 2 black dots, where there is no polarization, are called neutral points. And they were discovered in the early 1800s when, just after Malus first found polarization, and it was a hot topic to go around walking around with polarizers looking for polarization phenomena, Arago discovered a point in the sky opposite the sun, opposite the point diametrically opposite the sun. And a few years later, Babinet found this neutral point above the sun. Harder to see because the sun's bright and tends to blind you. And this pattern of neutral points tends to rotate rigidly around the sun. As the sun goes up, so does the Babinet point. The Arago point sets, and the point below the sun appears. And this was a point that was first discovered by David Brewster. Brewster was very interested in skylight polarization because it was a sort of phenomenon like polarized light, which he's well known for the Brewster angle, which is to do with the polarization on reflection. So what it means is that there are actually ought to be 4 points if we could see below the horizon, if it made sense below the horizon, and depending upon where the sun is, there are always 2 points visible above the horizon. By symmetry, the pattern below the horizon ought to be diametrically opposite the pattern above the horizon. These angles are typically about 15 degrees, and if we're able to resolve the lines of polarization near the sun, we would see a pattern, ideally, that looks like this system of confocal ellipses. So these neutral points, where you can't define the line, appear in quite a number of places. They're singularities of the direction of a director pattern, not a vector pattern, but a director pattern. As if you look in the top, if you look around one of these focal points, you starting below it, we're pointing, say, downwards. And as you follow as you pointing, say, downwards, and as we rotate around, we would be pointing out to the left, but following around here and coming back, we've only turned around 180, or the polarization direction only rotates around by 180 degrees, while as we turn a full 360 degrees around the singularity point. And so, unlike a vector field singularity, which turns around by 360 degrees, this 180 degrees comes from this director pattern. So here's what we see in polarization of skylight. Disclination defects in liquid crystals have a similar a similar 180-degree pattern. Here's an image of the principal curvature lines on an ellipsoid taken from the textbook by Hilbert and Cohn-Vossen. And again, there are isolated points on the ellipsoid, originally studied by Cayley and called umbilic points, which have exactly the same sort of nested parabola geometry, and at those points the principal curvatures are equal. We also see it in singularities in growth patterns. This is an image from the visual cortex, an experimental image taken from the visual cortex of, I think it's of a cat. And in the visual cortex, there are different cells which are sensitive to different orientation lines on that patch of the visual field. And those orientations are given by the colors in the map, as you can see in the scale on the right. But there are all sorts of points where all the colors come together, and all the colors come together at places where the direction isn't defined, which is just like the neutral points and the umbilic points in the other examples above. And even in fingerprints, you can find points where the direction isn't defined. There's a plus half tending to be at the fingertip, and actually one that's counter-rotating, minus half, which tends to be down from the fingertip and towards the thumb. So these patterns, these sort of nested parabola patterns, are utterly generic when we think about director fields rather than vector fields. So what do we expect the physics to look like for the light in the sky? So that comes from Rayleigh scattering, and Rayleigh scattering is the scattering of light by, say, the air molecules. When we have unpolarized light, this light from the sun coming in is unpolarized, it's vibrating equally in all directions, but as it scatters, it changes its direction. The light, as it propagates, as it vibrates, must always be perpendicular to the direction of propagation. So as the direction changes from S to S primed, the polarization must change from the perpendicular to S to perpendicular to S primed. And it turns out sufficiently far from the scatterer, we have exactly the same sort of matrix appearing as before. This sandwiching between two projections, projection perpendicular to S prime, sandwiching the matrix M. But unlike before, where M was attached to the crystal, what this M is, represents the mixture of all of the polarizations that we have. It's not a single polarized ray as we were thinking about before, but a statistical mixture of all of the different colors. So that statistical mixture starts off being uniform and circular, but after it's scattered, it gets squashed in the plane of the scattering, but does not get squashed perpendicular to scattering by this projection, because we're looking at this disk slightly from the side. And so if we think of not just a single scatter, but many, many, many scatters, it turns out that although we think that, well, maybe that sounds very complicated with a curved Earth, because the scattering length doesn't tend to be so long, we can actually approximate it very nicely, assuming that the Earth is flat. So if we assume that the Earth is flat, we've got a lot of scattering taking place, and we have a statistical mixture at each point in the sky, but there's a translation invariance associated with that. It means that actually each point in the sky is symmetrically the same as every other point in the sky. So when we look at the sky, we're simply looking at the same state, but from different directions. So what sort of state do we have? We have a mixture of polarizations, which in general, after many, many scatters, a mixture of polarizations that's represented by a certain ellipsoid. And when we look at the ellipsoid, what we're actually seeing is the polarization which is given by the mixture perpendicular to the plane of looking. So what we see is this ellipse effectively here. We have this mixture represented by the row 3, the statistical density matrix, and sandwiching it between these two projections, we get an effective polarization matrix in 2 dimensions perpendicular to S. So for all different directions of looking, we can pick out what is the apparent major axis, the main direction of vibration. And it turns out from this ellipsoid, looking in the direction, a given direction theta phi, I've drawn here the black line, which is the direction of the major axis that you'd see on that vibration. So in 3 dimensions, this cage, which looks just like the pattern we saw before, is just the pattern we get from the projecting the ellipsoid in those different directions. But as we have the same point, as saying the same, effectively the same ellipsoid everywhere in the sky by symmetry, all we do when we look is we're just looking at the same ellipsoid in different directions. So there's a sort of reciprocity between the light scattered from each single point, having this sort of polarization pattern, and an observer looking at this state, but from all different directions. The observer effectively sees this pattern around him or herself as well, leading to the same pattern of polarization that we have in the sky. So that's where we get the blue lines from in the model. It's simply fitting by this ellipsoid, and this is based on the approximations of flat Earth and so on. It's the delta shows the difference between the measured angle and this ellipsoid fit. It's not perfect, but it's a pretty good model to sort of describe what is going on. The biggest deviations are where the errors are large close to the sun, because the sun tends to saturate the detector. And that was an argument. Well, we used a slightly different mathematical argument based on conformal geometry when we proposed this in 2004, but it's exactly equivalent to this ellipsoid construction. And it's possible to take this a little bit further with a formal treatment of the radiative transfer of the light in the atmosphere. And it turns out the more formal treatment, considered as an expansion in mean scattering length in the atmosphere, indeed does justify this ellipsoid approximation that we were talking about. So this remarkable pattern of the polarization in the sky coming from the projection, it comes from the projection of an ellipsoid in different directions, just like the Fresnel ellipsoid construction for polarization through a crystal. And I've tried to explain why that should be and how that works. And here's what David Brewster had to say. He didn't understand why they were the same, but he did say, "It is not one of the least wonders of terrestrial physics that the blue atmosphere which overhangs us exhibits in the light which it polarizes phenomena somewhat analogous to those of crystals with 2 axes of double refraction." Oops. And as I say, what it's related to is this natural pattern of projections, this looking operator around this ellipsoid, or equivalently thinking about this tensorial decomposition of a real symmetric positive definite tensor in terms of its optic axes, or Maxwell multipole direction. And because we've got this polarization, we have this 180-degree turn around a point. It turns out that these patterns that I've been talking about show up in coordinate systems. The single neutral point looks like parabolic coordinates. A pair of neutral points looks like elliptic coordinates. And in fact, our skylight polarization pattern also occurs in the theory of coordinate systems is an example of conical coordinates. So the purple and green lines in each of these cases are the lines of constant coordinates in these different coordinate systems. And these coordinate systems have these a singular at the singular points or the neutral points. They also, the elliptic and conical, depend on a parameter, which is the separation of the neutral points. If you were to merge them, then they would end up coinciding with elliptic coordinates become regular plane polar coordinates, and the conical coordinates become spherical polars. But and they have the regular vector singularities in them, but these are all standard coordinate systems, for example, occurring when you separate the Laplacian in 2 or 3 dimensions. But returning to this polarization pattern then, we said that we can't see it with our eyes. And I wonder, if we could have seen it with our eyes, how much of this mathematical story of linear algebra and coordinate systems might have been discovered centuries earlier. But because we can't see polarization, we can only reveal this sort of pattern in science and not through mythology or poetry or love songs. As far as I know, nobody has tried to write a poem about this pattern, but maybe we should look at the poetry written by bees. Not only the blue sky is polarized, but it turns out the light coming to us from the cosmos is also polarized. So this is a representation of the cosmic microwave background reaching the Earth from the Big Bang. It's measured by the WMAP satellite in this case, and superimposed on it is that the white lines give the detected polarization of this light from scattered by the very early universe, and it has a distinct polarization pattern with its own neutral points. The angular resolution isn't so good because it's very hard to measure. More recent satellite, the Planck satellite, has measured the polarization in far more detail. The problem is it becomes clear that there's actually a lot of extra physics going on, not just from the cosmic microwave background, but from the galactic magnetic field and other sources that's affecting the polarization. So we can't necessarily just see the polarization of the polarization fingerprints coming from the Big Bang. But these patterns are there and are important in our understanding of the early universe. So to finish, I've talked about how the blue sky has a polarization fingerprint pattern, which is seen and used by creatures with non-mammal eyes. We've had a quick tour through optics of crystals via Maxwell's equations and scattering theory, and see how many concepts follow from the geometry of three-dimensional ellipsoids. We've seen how a uniaxial birefringent crystal might be used for navigation, and maybe was how this theory of Vikings using sunstones to navigate at sea. And we've seen how the skylight polarization pattern is close to that of a biaxial crystal, and how the geometry of the pattern is organized by these isolated topological neutral points. So with that, I will leave you to contemplate on the potential poetry of this skylight polarization pattern. Thank you very much for your attention.
Thank you very much, Mark. Are there any questions?
I have a question. So I was wondering, briefly you talked about the multipole expansion, and basically, if I understood it correctly, it's that this polarization basically should come from the dipole moment. And I was wondering, is there something like those patterns that emerge, etc., also for higher multipoles?
Yeah, so you can. It's so yeah. So I guess one has to be careful to not to get too many things confused. That effectively this polarization is associated with the dipole. What we're talking about here is a scalar valued field, but what we're really talking about when we talk about polarization is a vector value field. So we should be looking at not, if we wanted really to look at this pattern in more detail, we should use vector valued spherical harmonics or spin weighted spherical harmonics. It turns out that for every L, this pattern, if you're looking at a L polar radiation, there is this fundamental connection between the scalar polarization pattern and your L polarization pattern. Because our L for our polarized light is 2, that's why it's special for this case, but it only generalizes to higher multipoles if you're generalizing the symmetry of your vibration as well. So but there are a range of there are subtle connections if you look at vector spherical harmonics or their generalization.
Okay, thank you very much.
Well, I have 2 questions. Well, actually, I do. I have one curiosity is just historical and has to do with the spherical harmonics. I wonder if those were introduced exactly for the study of this type of problems. And the question about science is about the location. What's the location of neutral points? What that is that determined by the line of sight, the projection of what?
Okay, so to answer your first question, the spherical harmonic, it's interesting to look at in the history that the spherical harmonics, certainly, I don't know who first introduced them, but Maxwell is talking, this discussion is in his treatise on electricity and magnetism, where he uses the spherical harmonics as a basis for his expansion of his multipoles. Interestingly, all of that discussion is using real valued functions. They weren't using complex valued functions at all. Another interesting observation is Sylvester, when he wrote his paper, he's actually quite rude to Maxwell. He says, well, you know, what Maxwell did is he proved that on the slide, the second line implies the first line, that if you start with a directional derivative, you can always write it as a sum of multipoles. But you can't, he didn't prove you do it the other way around. That was what Sylvester did. He said, well, but this whole thing is very dirty because spherical harmonics are a very beautiful abstract mathematical concept. But something like the Laplacian is a disgusting physicist's object. And so we shouldn't be, you know, he's sort of sullying spherical harmonics by talking about the Laplacian. But it's interesting to think that, you know, the things that he talks about as really objects of physics rather than mathematics, we now appreciate as absolutely core to modern mathematics. So the feeling of what's fundamental in mathematics shifts historically, perhaps more than physics. So the the other question you were asking, Renzo, and I didn't perhaps go into it in a huge amount of detail, is why are the neutral points at the angles that they are? Let me just see if I have the extra. No, unfortunately, I don't have it here. So so effectively, what is happening is this ellipsoid that I was talking about is an object that comes from multiple scattering. And if you look, the ellipsoid that I've picked here is actually one that corresponds to a pattern very similar to the one in the sky. So what it is, it's a perturbation of that sort of flat disk that comes from the sun. But as it is scattered around, it gets thickened a little bit by scattering forwards and backwards. But it also becomes slightly longer in the vertical direction than in the horizontal direction. And it turns out that's due to multiple scattering in, as you say, you tend to get polarization perpendicular to the plane of scattering. And the depth of the atmosphere, at least of the Earth's atmosphere, is effectively about 8 kilometers, but the width of the atmosphere before curvature or extinction of light kicks in is about 300 kilometers. So there's far more scattering that takes place side to side than up to down, which tends to polarize just slightly more vertically than horizontally. And it turns out that the function that although there's only a small difference between the eigenvalues, the angle between these optical axes is a far more sensitive probe of that. It's a little bit like the roots of a quadratic polynomial. I don't have to change the constant term very much when I start with z squared. If I add a very small constant, the separation of the roots is rapid, and that's why the separation of the neutral points can appear large from what is only a very small difference vertically to horizontally. So it does depend on atmospheric conditions. It depends on the density of scatterers. And in fact, one atmospheric physicists actually sometimes use the angle between the neutral points as a probe of the impurities in the atmosphere.
Oh, I see. Okay, thank you.